It's always nice to start a presentation with a splash. So hi everyone, I'm Jenny and I'll be chatting to you about a new prototype wave overtopping measurement system called Wirewall and our ambitions to develop this further so it can be used to quantify the flood resilience of nature-based coastal schemes. If anyone has any questions, there's a list of my co-authors and our contact details at the end of this presentation if you don't join the live streaming of this session. The Wirewall overtopping system was initially developed to measure the speed and volume of waves that overtop a sea wall. Our aim was to collect measurements that enable us to validate and better calibrate the numerical tools used in seawall design. By reducing the uncertainty in overtopping estimates, we ultimately aim to reduce the overdesign of coastal schemes and create cost savings. To create new cost-benefit tools suitable for hybrid coastal schemes and the ability to monitor the attenuation of flood hazard parameters is required over storm and longer timescales. Understanding the flood resilience offered by nature-based interventions is the first step in developing tools that consider defence maintenance and flood damage costs. Such tools will allow coastal managers to compare the economic impact of different coastal schemes when planning new shoreline protection works. The prototype Wirewall system used capacitance wires to create a grid of sensors, 3 rows of 6 wires starting with wire 1 just overhanging the sea wall crest and wire 6 spaced up to 2 metres inland of the crest. The system was deployed in Crosby in the northwest of the UK during 8 spring tides with onshore winds. Overtopping data are calculated using pairs of wires. The speed of water travelling between 2 wires is first calculated and then the volume is calculated using the depth of the water connecting with the most inland wire of the pair. The example graph collected on the 26th of October 2018 shows the cumulative wave overtopping volumes distributed inland from the crest of the sea wall. The vertical line shows high water. We can see that on the flood tide there is a greater volume of overtopping than on the ebb tide. The sudden jumps in observation are when a single large wave or a rapid sequence of a few waves overtop the sea wall. The close overlap in values of wire pairs that have the same inland wire give us confidence in the results. Prior to field deployments, the Wirewall system was validated in HR Wallingford's flume for different wave and water level conditions over different duration tests. 3 large tanks were used to collect the overtopping volume passing through the Wirewall system. Volumes from the Wirewall master electronics, which is the row of wires positioned next to tank 6, and from the Wirewall slave unit, which is the row of wires positioned next to tank 4, plus volumes from the individual tanks are plotted. The black line indicates a 1-to-1 agreement with the volume collected in the central tank 5. The dotted black lines show plus or minus 20% uncertainty in the volumes from the middle tank. The volumes are as measured. They are not scaled up to real-world values. It can be seen that the agreement of the Wirewall units with the tank data is very good, usually within 20%. The tank data show that there are differences in the volumes measured across the flume for the same tests, which can generate more than 20% uncertainty in the volumes, accounting for much of the scatter in the measurements. The field data can also be presented as a time series. Again, we show data from the 26th of October as an example. This event didn't trigger a local flood hazard warning by the Environment Agency's numerical system, but from visual observation we are in agreement that an alert for pedestrian safety should have been issued. The alert threshold is plotted alongside our data and the numerical estimates from the most recent version of the Bayonet GPE wave overtopping tool that accompanies the current Eurotop guidance for coastal overtopping. We clearly see and observe the asymmetry in the overtopping discharge, which peaks before high water and rapidly drops off during the ebb tide. The numerical tool, plotted as the black lines, provides a mean estimate with uncertainty bounds captured by upper and lower standard deviations. The coloured symbols are the 400 Hz data from the Wirewall system, averaged over 5 or 15-minute time intervals. Wire 3, the green data points, was positioned just inland of the hand railing at the crest of the sea wall. We feel water passing this point is suitable to compare with a numerical tool to assess the estimate of the hazard to pedestrians. From the plot, we see the numerical tool underestimates the maximum hazard unless the large uncertainty bounds are considered, and it also estimates overtopping to occur for a much shorter duration than observed, which would influence the cumulative volume estimate typically used for new build design work. Following the successful deployments of the prototype measurement system, we are developing it further and working in new locations with different coastal infrastructure. We are moving from wires to rods to make the system more robust so it can be deployed for months at a time. We will be adding a telemetry system to allow us to gain health check information and also hazard alerts. This will allow us to use existing real-time national monitoring data to trigger our observations to efficiently use battery power and log data of interest. We will be testing the equipment in the southwest of England next year, where winter wave conditions are much larger. The system will also be reconfigured to measure the waves and water levels at the toe of the seawall, in addition to the overtopping conditions, to gain a much fuller picture of the conditions posing a hazard and to enable the validation of modelled wave transformations from offshore to the point of impact. Our aim is to demonstrate how observed real-time hazard alerts can supplement an online flood hazard warning system developed by the University of Plymouth. The data will be used to assess if false alerts or missed alerts occur and if the hazard thresholds are set appropriately. Alongside the wirewall system, a laser scanner will be deployed to capture the low water beach profile to ensure the model inputs are representative of the conditions, to allow a more thorough model validation, while also assessing the role of beach level in mediating overtopping hazard. The delivery of such a system provides the potential to be deployed where nature-based solutions to coastal management are being implemented. Port Phillip Bay in Melbourne is a location where mangroves are being re-established to damp waves prior to impacting the coast. The spatial variability of the mangroves within the forest and within the coastal conditions means a high density of measurements from the open sea to the land are of value to plan the continued planting of mangroves within the region. Using Jawbone as an example, at present wave attenuation is measured through the mangroves, seagrass and salt marshes using pressure sensors to monitor the change in coastal hazard. The sensors are placed in front and behind of each habitat type, and the height of the waves is calculated as the difference between the onshore and offshore pressure sensor, taking into account shoaling. Attempts have been made to compare the wave attenuation of natural or hybrid habitats against hard structures, in particular groins and rock revetments, using the same methods. However, these methods do not take into account the ability of the hard structure to reflect rather than attenuate waves. To date, there have been no studies comparing the overtopping of natural versus hard structures. Using the wirewall system would provide the potential to measure directly in front of a seawall to gather information about the total incoming and reflected wave conditions, in addition to the overtopping. Because the system itself uses low-cost sensors, this provides the opportunity to deploy in multiple locations across a region to see how different defences respond to the same storm event. In summary then, new versatile measurement tools are becoming available to measure a range of coastal hazard parameters. Wirewall is an example. The capacitance-wire approach is low cost and has the potential to collect data on the spatial variability of wave, water level and overtopping conditions along a sea defence and at different defences within the same region. Continued development of the prototype measurement system into a monitoring system would allow it to be deployed as a set of sensors in high density throughout a vegetated system and at the land-sea interface behind. Being able to monitor wave attenuation and the change in overtopping at a hybrid coastal scheme would allow the level of resilience offered by the natural defence to be better quantified and incorporated into cost-benefit analysis. Many thanks for listening, and if you have any questions, please don't hesitate to contact us.